السلام عليكم ورحمة الله. Again, this is Rafa Nuti from Higher Colleges of Technology in Mainz campus. Today, I will conduct a lab session about the GPS system or the Global Positioning System. Today, I will show you the components of the system. After that, I will show you how to operate or power up the GPS system individually. After that, I will show you how to insert waypoints for your flight using the GPS AV map. First of all, let us talk about the GPS system in our trainer. We have two components here. The first component is this one, GPS backslash R nav KLN. And this is the display of our GPS EKP GPS navigation display. And on the other side, we have GPS antenna connected directly with the GPS receiver, this one, KLN. This will translate the signal received from the GPS, and this message will show directly using this display. As you know, the GPS will receive messages from at least 4 satellites. After that, the message will come to this unit. This unit will convert this message to X, Y, Z position, longitude, latitude, and altitude parameters. This will send these parameters to the display to show us the actual position of the airplane. Now, how to power this system? As you know, we shall power these three circuit breakers. After that, click on the GPS breakers and the EKP display of the GPS. Now, after pressing these two circuit breakers, we can operate these two display. Let us start from the KLN 89. How to open it? Just you have to click here on this knob. Click on this knob. To increase the brightness, just rotate this knob clockwise. To adjust the brightness. Okay, that's enough. How to power the display? We have here power button. Just click on the power button for 3 seconds and it will open. After that, here click enter for any warning message. Again, click enter. After that, we should change the internal setup in this display. How to change the internal setup? Click on menu button. This is the menu button. We should wait. little bit. Okay, this is the menu. Again, click on the menu button until this list show in the display. We need to move the cursor, this one, until we reach to this point, system setup. After that, click on enter, go down by this cursor to fix setup, and then click OK. Change the fixed source from internal GPS enter to external air data, and that's it. Enter, and again clear, click here, clear, to go back to the main display. Now, go back to this, click OK for all these, for all the messages by clicking on this button, enter, enter, enter. Again, enter. Yes, we are here. Now we are finished now from the power output procedure. Now I will show you how to create flight plan using the KLN 89, this one. Our mission or flight will be starting from Muscat International Airport, OOMS. Then we will go to Salalah Airport, sorry, OOSA. After that, we will go to Marmul Airport, OONR. This is our plan. So we need to insert this waypoint in the KLN device, and we will display our flight simulation using the display AEKPIV. Let us come back to the device and let us start inserting the waypoints. First of all, look at the system. We have a lot of buttons here. Power, page, go to, zoom out, and in this corner we have the cursor. Go down, zoom in, menu button, enter in the green color. After that, we have clear to go back and cycle. And this is our display for the GPS system. Here, we have this small knob, push on to power on the system. After that, here we have two inner and outer knobs to select the waypoint. And here we have a lot of buttons. The first one, enter, clear, and go direct. We will use these three buttons today. And this button, CRSR, means cursor. Okay? Okay, now let us start to insert the waypoint. To insert the waypoint, take another look here. We have in the down, I think it's not clear. We have options here. Ox, set, flight plane. And we can move by this cursor, the inner cursor, to the flight plane. Go to the flight plan and then click on cursor. Now we are here. Now we will put the first airport, or using the outer knob. Using the inner knob, go to the next position. Again, insert O. Go to the inner position, go to the next, M. And the last digit should be S. After that, click enter. Once you click enter, look at this. The device will give you a lot of information about this waypoint. Muscat International Airport, Muscat, Oman. Okay, now click enter again to insert the second waypoint. Now we are in the second waypoint. The second waypoint will be Salalah Airport, OOSA. O, go to the next. Another O. Next. S. Next. The last digit should be A. After that, click on enter and look for this information. Salalah Airport, Salalah, Oman. Okay? Enter to confirm. The last point or the last waypoint will be O, O, N, R. Marmul. Okay. Now we insert the last point. After that, we have to click enter. This is the information or the location of the Marmul airplane. After that, go back to insert point number 4. But in this case, today we have only 3 points: Muscat, Salalah, and Marmul. Now go back to the first point. After that, wait. Maybe you forget to press. Click or press on direct. Direct, that's mean to start the simulation starting from this airport or this location. enter, and that's it. You can go here to set, not flight plan, go to set. Click on cursor and change. Sorry. Yes, change this one. This is the velocity of the airplane in knot, and this is the heading, the initial heading of the airplane. So put the airspeed 200 knot and click enter. Okay. Yes. Once you enter the velocity of the airplane, look at the display. Now, as we mentioned before, the data inside the GPS KLN specified. After that, it's transferred to the display to show us where is our plan. We are going to the first point. Once we reach here, the other point will appear and we will go to another point. This will simulate our flight path as speed, location, and XY, I mean longitude, and latitude, and Z, which is the altitude. All of these parameters, we can measure it or calculate it from the GPS system. Let me share you a video explain the principle of work of the GPS system.
Above sea level is a constellation of satellites, each orbiting Earth every 11 hours and 58 minutes. These satellites are continuously beaming data down to us on Earth, which is in turn received by devices such as your phone or navigational units in your cars, allowing you to see where you are on the planet. There are a lot of misconceptions about how GPSs actually work, an example being that your phone and the GPS satellites are both talking to each other. So let's get down to it. How do GPSs work? GPS stands for Global Positioning System, which works through trilateration, not triangulation or multilateration, which is commonly misconceived. There are many different types of navigational satellite systems from countries across the world, but the most popular and commonly used system is Navstar, which is the USA system. There are, however, Russian, Indian, Chinese, and European equivalent systems, although the Indian and Chinese systems sit in a geosynchronous orbit above their countries, which means they are not worldwide systems. The Navstar system, which is simply referred to as GPS, is what we will be focusing more on, although most phones and devices tend to have the capabilities to use both GPS and GLONASS. GPS satellites are set up in such a way that from almost anywhere on the surface of Earth, you should have a direct line of sight of at least 4 GPS satellites. This is quite important on the basis that GPS point positioning requires at least 4 satellites to calculate 3 position coordinates and the clock deviation. As GPS units are receivers, there needs to be something sending some sort of signal to devices such as your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth, which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5 1.5752 GHz and 1.2276 GHz. These two bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time difference with the speed of light, as the signal is sent at the speed of light, you can begin to get the distance away you are from that satellite. As these satellites are also sending whereabouts they are, you can begin to draw spheres around the satellites, with you being somewhere on the outer border of that sphere. As we introduce more GPS satellites into the mix, we begin to get closer to where we are. By calculating the time differences between these satellites, we move from having no idea where we are to being able to pinpoint where we are, typically down to 5 to 10 meters on average, with the potential error being around 15 meters. There are a lot of factors which escalate the potential error, but the most significant is due to the ionosphere, a part of the upper atmosphere extending from 60 kilometers to 2,000 kilometers, where free electrons occur frequently enough to have an appreciable influence on the proportion of electromagnetic waves passing through this layer. This error is substantially smaller when satellites are directly overhead, compared to being larger the closer the satellites are to the horizon relative to you, as the path between you and the GPS satellites goes through more of the atmosphere compared to being directly overhead. Even things such as small variations in the atomic clocks found on board these satellites can cause major errors. A clock error of 1 nanosecond can translate to a 1 foot or 30 centimeter miscalculation. Then the theory of relativity kicks in, with the atomic clocks ticking ever so slightly slower than clocks which are stationary on the ground, which translates into a 7 microsecond a day delay. General relativity then also kicks in, with the effect of the gravitational frequency shift being far greater than the 7 microsecond per day delay due to the velocity relative to Earth. As the theory states that a clock which is closer to a massive object will be slower than a clock further away, the atomic clocks on board the GPSs are faster by about 45.9 microseconds per day. Combining the 7 microsecond a day delay due to the satellite's velocity relative to Earth and the GPSs being further away from Earth, this adds up to a 38 microsecond delay, which if left uncorrected would translate through to a 10 kilometer a day pseudo-range error, rendering GPSs invalid from the get-go if this was not to be taken into consideration. This is compensated by the GPS's clock's frequencies being slightly slowed down from 10.23 MHz to 10.229999995543 MHz to cancel out the effects of relativity. So next time you turn on your GPS on your phone or other device, you should now realize just how much physics and maths is going in towards you finding your own location. Thank you for watching. Be sure to subscribe.
Okay, now again back to the system. Once your airplane reach to the final destination, you should clear all the points in the GPS to be ready for the next flight. How to clear the point? Using the inner knob, go to the flight plan section. After that, click on the cursor, move to the first, to the first waypoint. After that, click on clear. Enter, clear the second point. Enter, and clear the third point. Enter. And that's it. Now you can decrease the brightness of this device and pull it out to switch it off. And for this display, only click for 3 seconds to switch off the display and click enter for any alarm message. You have to click for 3 seconds on the power button. What else? Go to the circuit breaker. Pull up the EKP breaker, pull out the GPS breaker, and finally here also pull up the R unit 28 volt DC and the main power supply and these two switches, the first one and the second one. Thank you all for your watching. I hope I provide you a lot of information during these 4 lab sessions. Thank you very much and see you soon, inshallah. Thank you.